know him already, so I don't know if it makes sense to introduce him, but he's the CEO of our New Zealand office of Do It Now. And he's also going to talk about OpenCHAMI.
Okay, hopefully you can hear me. Thank you so much. So, well, the topic that I'm going to introduce today is what we have done over the last few months with OpenCHAMI. Basically, what we have done is integrating a single system image technology into OpenCHAMI. A bit of context of our journey in this particular software technology. So we wanted to evaluate the OpenCHAMI to see how well it performs and evaluate and compare to other existing softwares. So that's why we allocated one of the interns that we had at that time, so Luna Morrow. And she was doing everything very fast, faster than what we were expecting. So she was testing this, deploying a cluster in no time. And that's why we were thinking, well, let's do something else. Let's integrate this technology that we developed a few years back that allows to transform a cluster manager into a single system image provisioning. And with it, so I'm going to show you basically the motivations around that. If this works. Yeah, OK. So Massimo Benini already introduced OpenCHAMI a slightly bit. So let me work on this. So we already know that it's an open source management toolkit. The important thing is that it's a tool that it's pretty new. So it was founded on 2023. So we are talking about 3 years of lifetime, and has been built to target HPC, AI, and cloud. So this is basically ticking all the boxes of what we do as a company, as I do it now. So it's cloud native, so it's modular, it's container-based, but without losing that kind of tools that regular sysadmins have been working over the past 20 years, right? So as Massimo Benini was explaining, so there are multiple ways to deploy OpenCHAMI. One of them is using Podman couplets, which allows you to interact with a systemd. So this is perfect for regular sysadmins because they understand how this works. Okay. The only difference is that rather than installing the services on the host, you are installing it in microservices located into a container, but you don't see this. So all this complexity is gone. And it's already automated already. So because this is architected from the very beginning to meet demand on HPC and AI, you can deploy regular HPC cluster and Kubernetes cluster using the same infrastructure. In addition to that, you can deploy this on the cloud. So there is not that much need anymore on having multiple silos of software to target kind of different kind of deployments depending on what you want to do. And the beauty of this is that it's very infrastructure code-centric. So everything you do in the code, it can be reproducible, it can be applied into the system. It's very DevOps oriented. In addition to that, it's zero trust, has a zero trust approach. So if you go to traditional HPC cluster managers, so there's a kind of a SSH handshake, and you have to transfer all those SSH keys across the cluster in order to be able to access to the compute nodes and to interact with multiple services around that. So here, the status is different. It uses more modern technology, and it uses WireGuard and Cloud Init to make this possible. In addition to that, it supports a stateless and a stateful deployment. This is the part that we were interested in improving. And this is the story about that. So moving ahead to the next one. OK. So static images introduce some challenges. So if you are working currently with an HPC cluster with a traditional stateless or stateful deployment, you want to change one thing. You want to install a new RPM or a new package, and you have to go to the image, modify it, redeploy the cluster, right? So this is a problem. How you can somehow overcome to this problem and this challenge? So you add an Ansible playbook and you run it across the cluster, and then you will get the desired state, which is this new package into the system, right? Have you tried to do this at the scale? It doesn't work as expected. So this is the scalability issue that we are facing, right? In addition to that, if you want to have a consistent cluster behavior, if you're using a stateless, you need to reboot the system to get that. If you want to have something between, then you have to add Ansible or something like this to add those changes into place. In addition to that, so it really depends on the strategy that you use. But in a stateless deployment, quite often, so the common trend and the common approach is that you have the image, you stage the image into memory, which takes quite a significant amount of data into the network for every single compute, and then that goes into memory. So this memory does nothing. It's just OS. And it's a memory that cannot be used for compute. It's a very expensive thing nowadays. So have you seen the prices of memory teams? Yes, so that's not good. So this is it. Okay, so now there's an additional motivation around that. Okay, so what we want is it's something that we can run it once and forget about it. So this is the beauty of a single system image. I'm going to show you later in more detail, but basically, I can perform a change in the file system where the image is located, and that change, it's instantly available everywhere in the cluster, no matter the size. So there's no scalability issue because it's cluster file system. The problem is gone magically because the design, it's beautifully well designed for this. So if we compare, so I'm going to compare 3 of them. I had some other information about HP CMS before, but I think that because Massimo already disclosed and explained that it's nearly the end of the lifetime, so I'm going to focus on traditional provisioning on software that most of you know quite well. So Meta as a service from Canonical. So it allows you to do a stateful provisioning. You can do stateless as well, but you have to put a bit of effort. What this means, this 4 to 8 gigabytes and 1 to 2 gigabytes. So this means the data that you have to inject into the network in order to deploy the system. So you're going to get an image, and if you need to install the NVIDIA drivers and other stuff, so you go to 8 gigabytes easy. And you need to transfer this to the network. How many nodes do you have? You do the math. And then you know what in Fabric technology you need to provision a cluster with that amount of time. So the bigger is the cluster, the more it takes to deploy. And this is because the system is not able to scale as well as what we are looking for. So with Werewolf, it's exactly the same kind of a situation. There are some tips and tricks that you can incorporate in there. You have a traditional, so the vanilla and out of the box, it gives you a stateless. And again, so exactly the same size, between 4, 8 gigabytes of disk footprint that will stage into the node memory. So there's a strategy where you can split the image in order to reduce the size of the image, but also incorporates additional challenges and additional complexity. OpenCHAMI, out of the box, boots the kernel and init ramfs. So this relies on a squashfs, which gets staged into the memory. So we still have this memory footprint anyway. Now, what we have been able to achieve, and this is the motivation about that, is single system image. What it means, single system image. So it means that we are going to transfer into the network the Linux kernel, a modified, quite tuned init ramfs that has the drivers of the cluster file system that we want to boot from, and it will mount the file system in a read-only mode on the compute node, and it will boot from there. How many files do you think? So just a quick analysis, and this is an open question to the audience. So you have, imagine that you have 8 gigabytes of information in your image. How much megabytes do you think are going to be read when you boot the OS? So any taken? No? Very few. Very few. So, and that's the reality. So you boot the OS, and what is going to happen? It will go to the systemd, and it will, I'm going to start this daemon, I'm going to start this daemon, this and that. But SSHD, we are talking about few hundreds of kilobytes, things like this. So the amount of data that you have to access to from the image, it's pretty symbolic. But we have this overhead. So in this strategy, what we have is the image is not sitting locally. It's in a remote server. And it's a remote server for every single compute node, because all the nodes are going to access to the same files. The cluster file system, even NFS, will have this in cache. So it's going to be bloody fast, which is the next point. So lightning fast boot. So we are talking about the order of tens of seconds. You get the cluster booted. And it's completely independent to the size of the cluster, which is pretty awesome. And the other thing is that, as I was mentioning before, so this is a read-only file system, but you have read and write permissions on the cluster file system side. So you can mount the cluster file system in a read-only read and write mode. You can perform the changes there. You can do chroot, the path where you have this image, which is live, and you can change that image. Once you have done any change in this file system, everything, so all those changes are instantly available in the complete cluster-wide. OK, so moving ahead, what we are able to achieve is a really fast and reproducible way for node configuration and booting. In a single atomic operation, we can perform changes, so without any delay. There is no longer need to restart a compute node. So think about all the outages that you can save, or rolling updates complexity. So you don't need any rolling update after this. So there are some situations that, for example, if you have to add a file, a configuration file, and then you need to restart the daemon, you might need to restart the daemon anyway in all the compute nodes. But if it's just file system at the file system level, you don't need to do that. So if you think about all the security vulnerabilities that we have seen over the past few months, so all those issues could have been fixed right away in a single operation rather than having to progress this slowly into the cluster. And the beauty of this as well is that it's very DevOps friendly. So you can incorporate inside the chroot or inside the Ansible playbook running in a single instance. So you don't need to run multiple Ansible playbooks for every single compute node you have. You run it once. That's it. So what we did was the easiest implementation we could do. So we did root NFS. And it turned out to be really successful. So we had that already developed before. And so it's basically tweaking a slightly bit the drag code recipe to enable the rootfs to pivot to external file system. So out of the box, NFS has no high availability. So this is not suitable for a production cluster unless you have GPFS in the backend, and then you can expose this in a kind of a high availability and load balanced NFS environment. But the results were really, really impressive because we were able to put the system really, really fast. The next step that we did was with BZFS, because it's extremely easy to install, and it has high availability, it's suitable for production, and it also has RDMA support. This is perfect. So we tried it. It worked out. So we had the previous experience before because we did the same thing back in the time. So this introduced a bit of a delay, unexpected delay. So it was 85 seconds. But we are confident that after the bug, this is what we are working now. We can move this down to 30 seconds because it's what we were able to achieve before. And currently, we are working with cluster file system. So cluster file system is one of the standards in HPC cluster file system and AI clusters. And in the same way as BZFS, it also supports a high availability and RDMA. And this also guarantees the speed and the scalability that every environment like this requires. So how we did it? So we have basically the vanilla OpenCHAMI, but we don't want to do all the manual steps every time we want to incorporate a single system image, because now that we're happy with this, we want to move this, to translate this into a production-ready solution. We have clients that will like to use this. And so this is something that we need to somehow architect in a way that we can reproduce anywhere we go based on a vanilla OpenCHAMI. So what we did is to incorporate, to develop a simple script that runs, that modifies OpenCHAMI, and it's able to generate the single system image of the box. So with on the top side, we have so OpenCHAMI workflow. So it's an oversimplified OpenCHAMI workflow. Okay. So basically, it generates a squashfs. The squashfs, it gets transferred into the network to put the OS on the compute node, and it loads the image into the memory, and finally the node boots. Okay, so oversimplified workflow of OpenCHAMI, but it allows us to incorporate to show what we have incorporated on top of a vanilla OpenCHAMI. So when we say that it generates a single system image, what we are doing. So we are taking this squashfs that OpenCHAMI has already created, and we are using that as a baseline. So we generate a copy, we uncompress this squashfs, and we save it in the cluster file system. Then we go to the kernel, to the drag code, and we run it, and we basically injecting in the init ramfs the drivers and a bit of logic to mount the file system, pivot the file system into the new rootfs, and get the node booted to that. So and this happens, gets instructed in the init ramfs. Then what we do is we prepare the cluster file system client in the init ramfs, and we patch the OS in the image to become read-only. This is extremely important as well, because we are doing this for performance. We are doing this to make our life a lot easier. But now thinking this with the perspective, having a read-only file system makes your cluster a lot more resilient in terms of security, because you cannot modify everything. So if you try to modify a file that it's read-only, you won't be able to do it. So this makes this solution more security engineers friendly, if you know what I mean. And in addition to that, we still are using technologies like BSSS. So basically what we are doing is we patch the YAML file to instruct the system to boot from there. OK, so now we have the system ready. We can just go to push this new image, boot the custom RAMFS, switch the root, and get the node booted. So what we have achieved so far. So there are a lot of things. There's a lot on a list that you can compare traditional HPC cluster managers like ITSCAT or Werewolf or the NVIDIA VCM. But in terms of what we have been able to achieve, it's a faster cluster provisioning. So we are moving from gigabytes per node to just few megabytes per node. It's quite an impressive milestone. We have improved the resilience because if you go to the scale, we had a kind of a really nice presentation before. Mean time between failure on a disk, it's relatively short. But if you multiply this by the number of nodes that you have, the probability of having a failure in your data center, it's of order of days or weeks. So this is it. So if you don't have this, you don't have those failures. You go to the cluster file system. Obviously, those disks will potentially fail, but they are in a RAID. So it becomes the solution, the architecture, it's more reliable. And at the same time, this also reduces the cost of provisioning the cluster locally. Why? Because you don't need to multiply the cost of local disk for number of nodes that you have. In a centralized way, you end up with a lot less disk. Obviously, we are assuming a certain scale of cluster. When you are dealing with a relatively big cluster, there's a situation where you need to stabilize the system. And this is tricky. And if you need to modify things and get to try boot the cluster again, so if it takes like literally 15 minutes to get the cluster up just to try a minor change, it's crazy. So it's killing all productivity. Whereas in this kind of a situation, you just run the change, and you have the change already available in the cluster. So in terms of the back time, this is a lot faster. So for the people installing clusters, very big clusters, that want to review stabilize the cluster, the installation, this makes quite a huge difference. And as mentioned before, smaller memory footprint. We are moving from gigabytes to just few tens of megabytes. And that's me. Thank you so much.
Any questions?
Hi, Jordi. So how does this approach differ from the Statelite approach of XCAT?
So this is...
Because it's a bit similar. So what are the differences?
Yeah, so really good question. So with a Statelite, so there's something between stateless and a stateful, right? And it's Statelite. What is happening with a Statelite is that you have a portion of the image that gets booted in the nodes, that it's stateless, and then, stateful, and then the rest, it's on a remote file system. But because you're splitting the image, if you want to install, for example, an RPM that has to save things on the /etc and then /user bin, what kind of portion it's on the stage, on the stateless or on a stateful. So it builds this kind of additional complexity. It's exactly the same situation that we have with a werewolf when we split the image as well.
Yeah, well, as far as I have seen, the file system, I mean, part of the file system, part of EOS is mounted through NFS that is using GPFS as a backend for the high availability, and also to be able to export the file system from various nodes, so that gives the scalability.
Yep.
So in the NFS approach, is this? In your NFS approach, is this using more or less the same concept?
Yes. Yeah. So it's a similar approach. So you have actually the same design architecture. So you have IBM spectrum scale. So offering GPFS basically on top of NFS on top of a GPFS, and then you boot from there.
Yeah, and also I can see, and this is just a comment, I can see the advantage of using NFS over BGFS or Lustre is probably with BGFS and Lustre, those are parallel file systems that need to use a native client. So whenever you update the file system, Lustre or BGFS, you need to update the client as well.
Yes.
So with NFS, you don't need to update the client.
So, yeah, exactly. But there are some situations. So if you update the client, at the end of the day, you have to restart the cluster because it's a critical component of the whole thing anyway. And this is something you have to do this anyway on the current configuration that you are describing as well.
Thank you.
If everything's in the same architecture family, it saves you. What happens in a multi-architecture situation where you have ARM nodes and x86 nodes? And is there additional complexity, or is it just point them to a different location?
So actually, we haven't done this in OpenCHAMI, but we did something very similar. So for example, Decouple. So there is the management nodes are working on AMD microarchitecture, but they are booting ARM microarchitecture. And this is because we are using Docker, I forgot the name. It allows you to build an image based on that microarchitecture on a different microarchitecture. So you're using QEMU to simulate that architecture. So at the end of the day, there's nothing different from there. And this is completely independent to the architecture.
Okay, any other question?
So thank you, Jordi, and thank you, Miguel, also for mentioning the Statelight. One of the advantages of Statelight is that it allows you to write on the node. And call me a dinosaur, right? But there are several applications that require specific config files per node, right? How do you deal with that in your setup?
Important question. I forgot to mention it. So as part of this script, if you remember, I mentioned that there is some sort of preparation for the OS to become read-only capable. So you need to enable that capability at the OS level, and then you have to maintain a list of files that can be updated. So it's called etc read and write tab. And inside that folder, you have like configuration files where you can say this file it's eligible to be rewritten or being modified.
Yeah, so we used to have a similar setup at BSC long time ago. But we were using OverlayFS. That was part of the XCAD Statelight setup, which was also very useful. One of the problems that we saw with the single system image, it's very fragile.
That's the thing.
You have to be very careful with what changes you make, otherwise your whole system goes down.
So this is I had this conversation actually with other people from OpenCHAMI. because I know that there are some other institutions in the United States that they are taking this approach as well. So basically, they have an NFS root, but rather than using this approach that so read and write tab, they are using overlay FS. But if you go to the kernel nodes from Linux, they tell you that it's unreliable because, so it's not unreliable, the software itself. But if you modify the lower there, the results are unpredictable. So it's not a good practice to modify the lower there when this is exposed to a higher layer. So that's why this old school kind of strategy works really well for this. It comes with this additional overhead because you have to maintain this list of files that you can read and write on the compute node. But it allows you to safely modify and expose this read-only file system on top of this.
And follow-up question. So whenever you write to a file on a compute node, it ends up in a copy on write in memory?
It goes on memory. But rather than filling up like gigabytes of memory, you're filling up whatever change you add on that file. And usually it's configuration files. Because usually the logs, which could be quite large, go to a remote syslog server. So you don't need to inject data in there.
Thank you.
I think we're pretty much done. I don't know, Jordi, if you want to say some closing words for the day.
Yeah, so well, now we have the visit to the Barcelona Supercomputing Center. I believe that the bus will arrive around here in the next few minutes. I'm not sure if it's already here. We don't know.
I will ask.
So yeah, so please stay around, and we are going to inform you once we are ready to leave. We have been told that if you want to leave the laptop inside the bus and have a kind of a hands-free walk into the Barcelona Supercomputing Center, so that you can do that. The bus will be locked, and they are going to move us back, not here, but to the Ibis Meridiana, I believe. So you can collect then your laptop and your backpack from there. So it's up to you. Thank you so much.